Alright, so the next one we're going to do is problem 47 from chapter 18. So this is the diagram for problem 47. When a system is taken from state I to state F along the path IAF, the upper ones, let's see. The Q is 50 calories and what is 20 calories. So I'm just going to, because this looks very busy, so I'm just going to say that we have the IAF, which is the upper one. It tells you it has 50 calories, and the work IAF is 20 calories. Along path IBF, the lower part, the IBF, so you have the Q IBF, which is 36 calories. And so you also find what is the work along the IBF. Okay, so you want to calculate what is IBF, and then if the work is negative 13 for the return path FI, so I'm just going to say WFI, which is negative 13 calories. So what is the Q for this path? So you want to calculate QFI. Okay. And then you will also find if the internal energy at point I is 10 calories, what is the internal energy at point F? Okay, and if the internal energy at point B is 22 calories, what is Q for IB? So QIB and then QBF. So you can see that you have a lot of simple different paths, so it's very important that you actually write down the Q and W accounting the path, because they are path dependent. Okay, all right. So you're given IAF with this amount, that's 50. You're given the work that is given, that's 20, and then the IBF from I to B and F is 36 calories, and you also find what is IBF. So this is a typical problem when you have the you have the gases going through these processes. So we know that internal energy does not change, and based on the first law of thermodynamics, we know that the change in internal energy. So you have the IF, which basically doesn't really matter. You go from IAF or IBF. You have the initial, you have the same final. So you just the change in internal energy is from I to F. So I'm just going to say from I to F. That will be QIF plus the minus is Q minus W, so minus WIAF. Likewise, is also to be equal to IBF minus WIBF. Okay, so you can see that this is based on a straightforward applications of the first law of thermodynamics. The change in internal energy between I and F would just be the IAF minus the W and WIBF minus IBF. All right, so let's see. IAF is 50, and then WIAF is 20. So we know that the change in internal energy between I and F is 30 calories, and that has to be equal to the lower part here. This is 36, and then minus WIBF. So from this, we can actually calculate our IBF, how much work is done, and that will be 36 minus 30. So you'll get 6 calories. Okay, so IBF from I, B, and F, that takes the amount of work done by the gas is 6 calories. So I'm just going to write down here. So that's 6 calories. Okay, and then you also find the part B. What is if WFI is negative 13, what is the QFI? All right. So we know that the change in internal energy from I to F is 30 calories. This indicated that the change in internal energy from F to I, which you just reverse the direction from F to I, that will be negative 30. Okay? So from F to I, that's negative 30. Again, we're going to use that value. So this is negative 30. I'm just going to write it down here. That has to be equal to QFI and then minus WFI. Because, again, that is the applications of the first law of thermodynamics. QFI, we don't know. WFI is given, which is negative 13. So negative 13. So once you have that, you'll find that your QFI will be negative 30 and then negative 13. So you get negative 43 calories. So that will be QFI. QFI, that's negative 43. So I'm going to write down here, negative 33 calories. Okay? So this is basically how you how you calculate account for the amount of heat and the amount of work that's done by the gas. All right, and then the next thing you're asked to find. Let's see. What is the next thing you're asked to find? You're asked to find. Let me see, part C. All right. So if this is given, that's 10. What is this? And we just calculate that the change from I to F is equal to 30. That's from previously. So what does that mean? This means that will be the internal energy at point, the final, minus internal energy at initial. Okay, so 30 is equal to, this is the one that you asked to find, and then this is given, which is 10. So we found that the internal energy at point F, the internal energy at point F is equal to 30 plus 10, that will be 40 calories. Okay, so this has the numerical value of 40 calories. Okay, and then, let me see, what else? Okay, now if this point is 22, then we want to find what is the amount of heat between I and B, and then from B to F. Okay, all right. So based on this, how do we account for that? So we know that so let's start with IBF. So your IBF is from point I through B through F. So that must be equal to the sum of IB and then plus QIB and then plus QBF. Right? Okay. So IBF is 36 calorie. IB, QIB, we don't know. QBF, we don't know. We're asked to find. But at least we know that the sum has to be equal to 36 calories. And then what do we do with that information? So let's see. This has 10. This has 22. So if we get the change in total energy from B to F, that will be the internal energy at point F minus internal energy at point B, which we can calculate because this is 40. That is 40, and the internal energy at point B is 22. Okay, so this you can calculate that. Why do we want to do that? Because from B to F, that will be your QBF. Remember, again, that will be the first law of thermodynamics. The delta EBF is QBF minus WBF. Why do we want to do that? Because from B to F, there's no work is done because it's a constant volume. So meaning that this would just be QBF because that is 0. So your QBF would just be 40 minus 22. That will give you 18 calories. Okay, so this is how we calculate this. So that's 18 calories. And then we are ready to plug in this result to this equation because IBF is 36. And then QIB, you're asked to find. And then QBF is 18. So you'll find that your QIB is 36 minus 18. So you get 18 calories again. So you can see that this problem basically just a direct applications of first law of thermodynamics, that the change in internal energy is Q minus W, and then we also base off the fact that there's no work done when the volume is a constant, and then QIF is equal to negative of the change in internal energy from I to F is equal to the negative of the internal energy from F to I. Okay? So that is that. Alrighty. Alright, so the next one I want to do is problem 63. So let me erase this. Alright, let's see. Let me draw the diagram first. So you have the diagram like this. 1, 2. Alright, so 63. This figure shows that in a cross section, a wall consisting of 4 layers with thermal conductivity K1. So this is your K1, which is 0.06 watts per meters per Kelvin, and you have the K2, which is unknown, and you have the K3, which has a value of 0.04, and then you have the K4, which is 0.12. Okay, so these are the thermal conductivity. The layer thickness, your L1 is 1.5 centimeters, and then your L2. Your L2 is 2.8, L3 is unknown, and then L4 is, L2 is unknown, but then L3 is 2.8, and then L4 is 3.5 centimeter. The known temperature, T1, so at the interface, T1 has a temperature of 30 degrees Celsius, and then T12, the interface, T12 has a temperature of 25, and then T4 has a temperature of negative 10 degrees Celsius. Energy transfer through the walls is steady, meaning that the conduction rate is the thermal conduction rate is a constant value. So you ask to find what is the temperature, the interface temperature T34. Okay. So based on this, we know that energy. So this has a higher temperature. And you can see that the temperature gets smaller and smaller until you reach the ends. And then through this different material, the thermal conductivity has a different values, and the thickness also has a different values. T2 your K2, L2 are unknown, and we are not given this temperature. And based on this information, you wanna find what is the temperature between these two layers. So how do we do this? The only thing we know is that the conduction rates, which is this equation, is equal to K times the cross-sectional area, and then times the higher temperature minus the lower temperature over the thickness. So this P, conduction rate, has to be equal to each other throughout these layers because the energy transfer is steady. So what does that mean? It means that you will apply this equation at this interface, that interface, and that interface, and then see what we get. All right, so how about let's do that? And then because they all have the same area, so I'm just going to have the conduction rates over the area. So we just have the K. So in other words, that will be K and then TH minus T core over L. Okay, apply at each interface. So that's applied at the first one. So first one you have the K1, and then the higher temperature is 30, the lower temperature is 25, and you have the L1. So I'm just going to use the symbol for now. And that has to be equal to applying at the second interface, that will be K2, and the higher temperature is 25, and then minus the T23, which we don't know, over the length of L2, which we don't know, and that also has to be equal to when you apply to the third interface, which is K3. K3, and then the temperature will be K3 at this point. That will be T23 minus T34 over the length L3. And that also has to be equal to applying at the last interface, which is K4. And then the higher temperature will be T34 minus the lower temperature, which is -10. Okay? And then over the length, which is L4. So you can see that this has to be equal to this, has to be equal to this, has to be equal to that. And because in the problem you also find what is T34. So all this you can just ignore. We don't even have to go through that. We just say that this is equal to this. So you have the K1, and then 30 minus 25, that gives you 5 over L1. That has to be equal to K4, and then T34 plus 10 over L4. So now you can just plug in the number you were given. So K1 is 0.06, and then 5 over L1, which is 1.5. K4 is 0.12 times T34 plus 10 over L4. L4 is 3.5. So after you plug in, clean up the stub, you'll get that. After you do the algebra, you'll find that T34 plus 10. That's equal to 5.83, indicating that the temperature between the interface would be -4.167 degrees Celsius. Okay, so this is based on the conservation of energy, and then the rate of change, the conduction rate is the same across the areas. Through different layers, and the area is the same. So you can just base off this equation, and then I just say that the conduction rate over the unit area would just be the thermal conductivity times the temperature difference over the length of the thickness of the material. Okay, alrighty.